Our presentation will start with the problem statement, overall system design, followed by the three causes part. The conclusion and the reflection will mark the end of our presentation in this video.
Hi, I'm Tivia. Using steam methane reforming technology, the REX Energy Engineering Bihar is interested in producing hydrogen from natural gas. The company is now opening a tender for the project. So the objective of this project is to design hydrogen production of 30,000 tons per year with a purity of 99.9%. Therefore, the task given to us is, as a group of engineers, we are required to meet the tenders.
Hi, I'm Monroe, and this is our overall system design to meet the specifications set by the company. We decided to use 2 packed wet reactors to produce desired amount of hydrogen and 2 adsorption units to obtain 99.9% purity of hydrogen. Other unit operations such as heat exchanger, compressor, and valve are used to control the temperature and pressure of the stream so that the plant is working efficiently.
In SMR process, the use of catalyst is mandatory. Nickel-based catalysts assure an acceptable high activity and low cost. Nickel is one of the most widely used active pieces in catalytic partial oxidation. It possesses a very high reactivity and low accretion, as well as can withstand a very high temperature. It also exhibits a good mechanical strength. The chromium in ferrochromium oxide in high-temperature water gas catalyst has been used as a tensile promoter to prevent thermal settling of ferrous oxide. The ferrochromium mixed oxide catalyst is used because of its high activity, durability, and reasonable manufacturing cost. It also has the ability to dissociate water molecules. And the centering of this catalyst leads to a lower surface area, reduction in porosity, as well as increase in particle size. The multitubular fixed-plate reactor, also known as the PBR, is used for both directions because it has more conversion using lower amount of catalyst, it has a lower operating cost, and the operation is continuous, as well as it has a minimal catalysis losses, as well as protect contamination. The strategy to maximize the selectivity and yield of hydrogen, as well as to minimize the side reaction. First of all, we can increase the reaction temperature at constant pressure, because according to Raychaudhuri principle, an endothermic reaction forward reaction favors a very high temperature condition, and the overall heat of reaction in this process is endothermic. So it requires more energy to be absorbed for the reaction to take place efficiently. Therefore, the methane conversion rate and hydrogen yield will increase with increasing reaction temperature at constant pressure. Besides, we can also decrease the inlet pressure because according to Raychaudhuri principle, the increasing of stoichiometric number in reaction can be favorable in low pressure because gas molecules of product is higher than the reactant. Therefore, low pressure will favor in the forward reaction. So, increase in conversion of methane and greater hydrogen of yield can be observed. Next, we can increase the steam to carbon feed ratio and carbon dioxide to carbon feed ratio because a positive effect on the WGS equilibrium, which favors the production of hydrogen as well as carbon dioxide, can be observed. It reduces the hydrogen partial pressure in the reaction zone, and a pure hydrogen flow rate can be recovered. Therefore, it increases the steam to methane ratio, increases the hydrogen production by favoring reforming reaction. So, how the reactor separator system work for the SMR process? First of all, the natural gas stream is first passed through the compressor, and water is passed through the pump. Water must be in the form of steam, and natural gas is heated up at a very high temperature. The hot natural gas and the steam is mixed in the mixer during operation. Then, the methane reacts with the steam to produce hydrogen and carbon monoxide in the SMR reactor. After that, the temperature of flow out of SMR reactor is reduced. The carbon monoxide from the SMR reaction enters the water gas ship reactor. The hydrogen is then captured while the oxygen joins with the carbon monoxide to produce carbon dioxide. After that, the gas mixture exiting from the WGS reaction needs to be purified and refined to meet the customer specification.
As introduced before, we decided to use 2 reactors in our design. In the first reactor, methane and steam react to form carbon monoxide and hydrogen. The reaction is endothermic, thus it operates at 700 degrees Celsius and 25 bar. Assumption made are it is a first order reaction according to the literature, ideal gas law obey, and negligible pressure drop across the catalyst bed. Before calculating the flow rate and concentration of each component in the stream, volume expansion factor, conversion, and ratio between the reactants has been identified. Stoichiometry table then constructed as the app to calculate the flow rate and concentration of each component. To determine the reactor sizing, we follow the 5 steps. First, deriving the mole balance, the red law, list down the stoichiometry equation related, combine all the 3 steps, and evaluate it. Next, in WGS reactor, carbon monoxide produced before it reacts with the steam to produce hydrogen and carbon dioxide. The reaction is exothermic, thus it is operated at 400 degrees Celsius and 10 bar. We assume it is a first order reaction based on the literature. Ideal gas law is obeyed and negligible pressure drop across the catalyst bed. Volume expansion factor, conversion, and ratio between reactants has been calculated, and it is used to calculate the concentration and flow rate of each component based on the stoichiometry table. The 5 steps is again applied to determine the WGS reactor sizing.
For process modeling and simulation part, we were asked to complete 3 tasks. First, we would have to simulate the steady-state reaction process using symmetry software based on process parameter from reaction engineering part. Next, we would need to validate the simulation by comparing with manual calculation and provide deviation error between the simulation and the manual calculation. Lastly, using case study function, we were assigned to perform sensitivity analysis by discussing the effect of several parameters on the reactor performance. First, for the symmetry simulation part, the non-ideal plug flow reactor PFR is the reactor used for the SMR reaction in the simulation, with the assumption that the packed bed reactor PBR behaves identically to the PFR. 1852.50 kmol per hour of water and 650 kmol per hour of natural gas supply with 95% methane are among the feed streams. A pump transports the water stream before passing it through a heat exchanger, which elevates the temperature from 25 degrees Celsius to 1000 degrees Celsius at a pressure of 2050 kPa. The methane was pumped into the compressor, which increased the temperature to 300 degrees Celsius and 2500 kPa before passing it through the heat exchanger, which raised the temperature to 700 degrees Celsius. The heat exchanger and natural gas exit streams are then sent into the mixer, allowing the input materials to interact. The midstream is then fed into the SMR and subsequently fed into a cooler. The cooler is then connected to the output reactor or WGS PFR, lowering the temperature to 350 degrees Celsius, and we can determine the parameters in the outlet stream of the reactor. For the second part, which is validation through manual calculation, the simulation of both reactors which are SMR and WGS-PFR were verified. SMR-PFR, for example, by using the parameters that were obtained through reaction engineering part, as well as assuming the value of conversion, which is 0.83, we can determine whether the simulation is valid or not. By combining all these equations, which are the volume of SMR, rate loss, and concentration of methane, we can get this final equation. Compare the value obtained from this equation with final concentration known from the simulation, we will get a deviation error of 1.98%. For WGS-PFR, the steps to calculate the deviation error is similar to SMR-PFR. We will start off with the parameters as shown here that were obtained in CEB 2043 along with assumed conversion rate value, which is 0.28. Combining all these equations, and we will get the final equation. Compare the value gained with final concentration of carbon monoxide from the simulation, which is 0.01377 kmol per meter cube. We will get a deviation error of 42.75%. Lastly, for sensitivity analysis part, several parameters have been studied based on the simulation to better understand the impact they have on the reactor's performance. The independent variables for this topic are pressure, temperature, and feed composition. Meanwhile, the mole fraction of produced hydrogen and mass flow rate of hydrogen product at outlet stream are employed as metric to assess the reactor's performance. The effect of first parameter, which is the inlet pressure of natural gas on outlet mole fraction of hydrogen product, was studied. As you can see in the graph, the entrance pressure of natural gas is directly proportional to the output mole fraction of product hydrogen. The mole fraction of hydrogen will grow when the pressure of natural gas increases. Natural gas, or the methane, consumption is favored in a high pressure zone in the membrane reactors. As pressure rises, natural gas consumption rises, resulting in an increase in hydrogen production. Next, the effect of inlet temperature of natural gas on outlet mole fraction of hydrogen product was studied. The input temperature of natural gas is exactly proportional to the output mole fraction of product hydrogen. The mole fraction of product hydrogen will grow as the temperature of natural gas rises. High temperature encourages hydrogen generation in both conventional and membrane reactors. As the temperature rises, the average kinetic energy of molecules rises as well, resulting in more effective collisions. It also cuts down on the time it takes for molecules to reach the minimal kinetic energy required to overcome the activation energy. As a result, the mole fraction of hydrogen increases as the temperature rises. Lastly, the effect of feed composition on mass flow rate of hydrogen product at outlet stream. As illustrated in the graph, the mass flow rate of hydrogen product at outlet stream for WGS-PFR increases when there is increasing trend of natural gas inlet feed stream molar fraction. Increasing the mole fraction of natural gas, specifically methane, in the feed stream raises its concentration, which enhances production of hydrogen in WGS-PFR.
The adsorption column is used in the hydrogen enrichment unit to further purify hydrogen composition from the compound stream. The carbon dioxide removal unit's compound will be transferred to the hydrogen enrichment unit, where unwanted components will be removed using the adsorption process. The light and heavy unwanted components that remain in the stream can be removed based on different adsorbent. As a result, the natural gas can yield a higher percentage of hydrogen. Water, carbon dioxide, carbon monoxide, hydrogen, and methane are all present in the gas stream when it enters the adsorber. Therefore, two types of adsorbents will be used to enhance hydrogen generation with a purity of 99.9% by eliminating the unwanted compounds. The first adsorbent is activated carbon, and the second adsorbent is zeolite. The hydrogen enhancement plant's first adsorbent will be activated carbon. The characteristics of this adsorbent are it has small pores of various size, typically between 2 and 500 angstrom, and high specific surface areas of between 800 and 1400 meters squared per gram. The advantages include lower cost and suitable for waste streams containing wide range of VOC. Meanwhile, the disadvantages are it is not effective for VOCs with high polarity, not effective for highly volatile compounds, high annual cost for regeneration when used for concentrated waste streams, and degrades during desorption cycles. The second adsorbent will be zeolite. The characteristics of this adsorbent are it has uniform crystalline structures with uniform pores. The pores are smaller than those in activated carbon, and it also has specific surface areas comparable to activated carbon. The advantages of zeolite include it is highly selective VOC removal, good at removing small, highly polar and very volatile compounds, longer life, and less susceptible to degradation. Meanwhile, the disadvantages include higher initial cost and not suitable for waste streams containing wide ranges of VOC. The type of isotherm that fits the adsorption equilibrium data is Langmuir adsorption isotherm. The Langmuir adsorption isotherm is used to describe the equilibrium between an adsorbate and an adsorbent system in which the adsorbate adsorption is confined to one molecular layer at or before reaching a relative pressure of unity. Langmuir isotherm is chosen as it is mostly useful and valid at low pressure and high temperature. This is the computation for Langmuir model. The calculation starts with the left equation, where Q equals the concentration in solid, C concentration in fluid, and K is the equilibrium constant. The parameter in the computation is changed from concentration to pressure because the inlet stream of the adsorber is gas. Therefore, the equation is changed into the right one, where B is the parameter in Langmuir equation, P is the adsorptive pressure, and delta H is the change in the heat of adsorption. The product stream from the reactor contains few components, thus the type of components should be considered while determining the model's isotherm. We identify the concentration of adsorbate in solid, heat of adsorption, and adsorptive pressure for each component from the experimental data to compute the isotherm of each component in adsorber. Based on the Langmuir isotherm parameters, we can obtain the QE versus PI graph. The graphs below show the adsorption isotherm of hydrogen, carbon monoxide, carbon dioxide, and methane, respectively on activated carbon. The adsorption capacity calculated from the breakthrough curve experiments are also in good agreement with the volumetric equipment. Therefore, as you can see from all these graphs from the journal reference, majority of the components in the adsorber are following Langmuir isotherm. The Langmuir isotherm was used to fit the adsorption capacities acquired from the various feed components, and it was discovered that carbon dioxide is the most adsorbed gas, followed by methane, carbon monoxide, and then hydrogen.
Firstly, 3 coolers were used to decrease the temperature of WGS effluent from 400 degrees Celsius to around 200 degrees Celsius. Now this is done to ensure that the temperature meets the working temperature for activated carbon. A valve was also used, which was used to reduce the pressure of WGS effluent from 952 kilopascals to 100 kilopascals, which is the desired pressure of 1 bar. After that, the mass transfer zone, or MTZ, is calculated for each column by first acquiring the breakpoint at breakpoint concentration C/C0 equals 0.01 and the point where C/C0 equals to 0.5. So let us take a look for the case of activated carbon. After obtaining the values for TB and TS from the breakthrough curve, the used bed length HB was calculated. Then, unused bed length HUNB was calculated by subtracting the HB from the HT. So at this point, the scale-up principle is applied. This principle states that the amount of unused solid, or length of unused bed, does not change with the total bed length. So therefore, HUNB equals MTZ, which is calculated as 0.76 meters, where HUNB depends on the velocity of fluids. The same calculations and explanations are used in the case of the zeolite adsorbent. In the design parameters, both adsorption column types are PSA. They are also made from stainless steel, and its configuration is 10 bed 11 steps. This is so that a high purity of hydrogen gas can be obtained at the outlet. Now the rest of the remaining parameters are obtained from literature. The next step taken is the calculation of molar flow rates for AC, the activated carbon, and zeolite. This is done as follows, so that it can be used in the mass balance subsequently. Before conducting mass balance for the adsorption columns, the purity of hydrogen at the outlet streams are first obtained from a journal by Riboldi and Boland. Alright, so now we have reached the point where we calculate the mass balance for the adsorption columns. The first step is to develop the equations. Then substitute the values into the mass balance equations. At this point, F3 is multiplied by molecular weight of hydrogen, and by unit conversion as well as multiplying by the number of seconds in a year, we can finally obtain the amount of hydrogen required per year. Now that we have reached the amount of H2 production required per year, we will now be explaining the ways or strategies that can be used to achieve that 99.9% purity of H2 production. Firstly, we can increase the pressure of feed. Gases will tend to adhere to the adsorbent surface at high pressure. This is because of the increase in the force acting between the gas molecules and the absorbent material. Now, because sustaining excessively high pressure conditions is expensive, pressures should be kept at moderate levels. Next, increase the number of adsorbent beds. That way, more solids can be absorbed in the process, which in turn increases the purity of hydrogen. This is because the increase in bed number also increases the contact area between adsorbate and the adsorbent. Finally, we could conduct a recycling process by regeneration. Regeneration is required to overcome the activated carbon's capacity limit and allow it to work effectively in a continuous process. Regeneration of activated carbon is a thermal processing method for removing adsorbed elements from the surface of the activated carbon. To compensate for the losses, the equivalent amount of fresh activated carbon must be given when waste carbon is regenerated.
The project to design hydrogen production system in a big scale of 30,000 tons per year with a purity of 99.9% by utilizing SMR technology has been successfully done. The main objective of the design is to have a higher conversion of natural gas to produce more hydrogen. Besides, the plan design is also needed to comply with economic feasibility. In designing this process plan, chemical engineering knowledge have been applied throughout this project, which include reaction engineering 1, process modeling and simulation, and separation process 2. Reaction engineering course plays a vital role in optimizing the reactor's design for the reactions that occur in the steam methane reforming process. As a recap, the SMR technology consists of two main chemical reactions, which the first one is SMR reaction and the second one is WGS reaction. The type of catalyst chosen for the first reaction is nickel-based catalyst, and for the second reaction, iron-chromium mixed oxide catalyst. Besides, the type of reactor chosen, after considering the type of catalyst and phase involved, is multi-tubular fixed bed reactors. Big bed reactor (PBR) is the most ideal for the stated reactions. The calculation of the reactor sizing, flow rate, and concentration of each stream has been carried out based on the mole balances in terms of conversion, rate loss, and stoichiometric concepts to obtain the appropriate sizing. Besides, the strategy suggested to maximize the selectivity and yield of hydrogen and minimize the state reaction include increase the reaction temperature at constant pressure, decrease the inlet pressure, which is the reaction pressure when temperature is constant, and increase the steam to carbon feed ratio and carbon dioxide to carbon feed ratio. Next, for process modeling and simulation will run using the Symmetry platform to optimize the steam methane reforming process. However, due to the software's limitations, various assumptions were made in the simulation. The non-ideal plug flow reactor (PFR) is the reactor used for the SMR reaction in the simulation, with the assumption that the back bed reactor (PBR) behaves identically to the PFR. In plug flow reactors, the steam methane reforming (SMR) and water gas shift (WGS) processes were modeled. Several parameters have been studied based on the simulation in order to better understand the impact they have on the reactor's performance. The independent variables are pressure, temperature, and feed composition. Meanwhile, the mole fraction of produced hydrogen and mass flow rate of hydrogen product at outlet stream are employed as metric to assess the reactor's performance. Based on the sensitivity analysis done, this conclusion can be made. The higher the pressure and temperature, as well as molar fraction of natural gas at the inlet feed stream, the overall amount of hydrogen produced will also increase, hence higher yield of hydrogen can be obtained. Lastly, for separation process, an absorption unit is utilized to separate carbon dioxide from gas mixture, which is the effluent stream of water gas shift reactor. A pressure swing absorption (PSA) is used for the removal of carbon dioxide, methane, carbon monoxide, and water from hydrogen. The absorption column is used in the hydrogen enrichment unit to further purify hydrogen hydrogen composition from the carbon dioxide removal unit compound stream, where unwanted components will be removed using the adsorption process. Two types of adsorbents are used to enhance hydrogen generation, which the first one is activated carbon and the second one is zeolite. Moreover, the type of isotherm that fits the adsorption equilibrium data is long-way adsorption isotherm. For the adsorption column design, the total height of adsorption column was taken as 2.33 meter and the diameter is 0.62 meter, based on our journal reference. From the calculation, the mass transfer zone and TSAC are 0.76 meter and 0.71 meter on activated carbon and zeolite adsorbents respectively. For this project, we successfully managed to produce 30,000 tons per year hydrogen via SMR technology. The exact mass flow rate of our outlet stream is 30,034 tons per year hydrogen. In addition, some strategies to achieve 99.9% purity of hydrogen production are also suggested. This includes increase the pressure of it, increase the number of adsorbent bags, and recycle via regeneration.